this is our review for our quiz 7.1 review. Hopefully I won't have to go as fast as I did in class today since we didn't get to all the problems. Okay, so we're going to have y equals 2 times 2 to the x power. So try this one on your own and then come back to see if you have the right answer. Here's a little hint to get started. Plug it in your graphing calculator and set and go to the table. Okay, this is the graph you should have ended up with. We have our chart xy. We plugged in the points -1, 0, 1, and 2 for our x, and we got out 1, 2, 4, and 8 for our y values. We graphed them, drew the red exponential graph. We figured out our asymptote because there's no Kelly point is 0. So y equals 0. This is my little green line. If you can see that, I know it's hard to see on the axis. So our asymptote, remember, it's not just 0. It's y equals 0. Our domain means what type of values can we plug in for x. In this case, because the arrows go in both directions, our domain is all real numbers. In our range, we start at 0 and we go up from there. So our range is y is greater than 0. Why is it not equals to? Ask yourself. Ah, that's right. It's because it doesn't touch the asymptote. An asymptote can never be touched or crossed, so it comes close, very, very, very close to 0, but it does not cross it, so we cannot have that equal sign there. Okay, next one. Y equals 3 times 2 to the x minus 1 power. Again, pause the video, try this one on your own, get your graph, and come back and check your answer. All right, this is what your graph should look like. Your exponential graph is here in green with our table off to the right-hand side. Our asymptote this time, again, is 0 because there is no Kelly point, so that is in red on our graph. So our asymptote is, again, y equals 0. If you just plug 0 down, it is wrong. You'd have y equals 0. Our domain, yet again, is all reals. And our range means what type of values can we get out for y. And again, everything is above this line, so it's going to be y is greater than 0. Okay, one last one of these, but this one's going to be a little bit trickier. So we see our equation to begin with, 2/3 times 3 to the x plus 1 minus 4. And we see that we have an actual asymptote this time besides 0, and that's so exciting. What is it, you might ask? Well, what is our Kelly point? Our Kelly point is this point back here at the end. So our Kelly point is -4. So our asymptote is going to be y equals -4. We're going to graph that right away with a dashed red line. Okay, hit pause. See if you can do the rest of the problem doing your XY chart. See you in a few. Okay, this is what our graph should look like here in blue. Again, it comes close to crossing the asymptote, but never, ever, ever does. We have the points -1, -3.3, 0, -2, 1, 2, and 2, 14, which is a little high for the graph, but I just fit it in. Our domain, again, is all reals because you can plug anything in. And our range is y is greater than -4. So that's graphing exponential growth equations. And now we're going to do a real-world application problem. I know you're all so excited. Here we go. You deposit $8,500 in an account that earns 4.6% annual interest. Find the balance after 3 years if the interest is compounded weekly. How many weeks are in a year? Round to the nearest cent. Okay, again, in our equation, we know that P stands for principal. That's the starting amount. R is your rate, which is your interest rate, written as a decimal, not as a percent. N is the number of times per year it's compounded. And then in our exponent, we have the n again. And then our t, which is time. How many years are we talking about here? So give this one a try. Plug everything in and then come back for the explanation. Okay, now that you've tried this problem, you should get the answer of approximately $9,757.20. My actual answer I got here is going to be a little bit off of that. But anywhere approximately close to that, it's all going to depend on how you rounded. You might have rounded to 3 places instead of 4 like I did, or 4 instead of 5. That's all. I will notice that when I'm grading it, so that's okay. If you're a little off, that's fine. So if you got somewhere close to that answer, you can skip on to the next slide, but the next slide is also another one of these, so give that one a try. If you did not get this, around 97.57 as your answer, this is how I got that. So we start off plugging everything into our formula, knowing that there's 52 weeks in a year, so that is our n. Plug everything in, making sure again we write our decimal, or our percent as our decimal, so it's 0.046 and not 4.6. Make sure you move the decimal point. Okay, our next line in green here, we divided out the 0.046 divided by 52, and then added it to 1, and we got the 1.00088. And then we multiplied the exponent and got 156 as our exponent. Then we do our exponent part, and 1.00088 to the 156th power gives us 1.14708. And then we take that by our original $8,500 that we started off with. And this time around, I got an answer of 9,750.18. So as you can see, I'm a little bit off from our original answer that I got last night when I wrote the slides. But that's okay. That just means I rounded. I had one extra decimal place. I rounded to 4 places instead of 5, or 5 instead of 4, something like that along the way. When I'm grading that, I will understand that, and as long as you're approximately close and have shown your work, that will be okay. Okay, so let's give another one of these a try, because these are lots of fun, and these are ones that you will use in life. So here you go. Try this one. Hit pause, give it a try, come back for the explanation. Okay, we should have gotten approximately around $2,397.02 as our answer. If you got that, yay! If not, here's the explanation. Our percent is 0.0215. Compounded quarterly means 4 times a year, so that's where we get this 4 in both places. We do the inside of the parentheses first, and we end up with 1.005375. And then that's now to the 16th power. That is our next step. We take that to the 16th power. And we get 1.089566. And then we take that times the 2,200. And this time I came up with $2,397.03. I was just 1 penny off from what I was before. Again, as long as you're relatively close to it, you're good to go. Okay, now we're going to try a couple exponential decay problems. I know this is a decay problem right away. Why? Think about it. Got it? It's because what's in the parentheses here, what's being raised, is a fraction between 0 and 1. That tells us it's an exponential decay problem. So give this one a try. See if you can get it. Okay, here's the graph we should have come up with. Again, we realized from our original equation that we have an asymptote as +1 from our Kelly point. So we drew that in a dashed blue line on our graph. We do our XY chart. Usually when we have an exponential decay, we want to do an extra negative number in our XY chart. But in this case, not really going to work out for us here, because that gives us the point of -2,129, which sure as heck is not going to fit on this graph. And then we're going to do -133, which still does not fit on the graph. So then this graph only has 2 points. We have the point 0.9. And then we have the 0.13, but because we know what an exponential graph looks like, we know that it travels down and to the right. Again, coming close to touching the asymptote, but never ever touching it. So our asymptote is y equals 1. Our domain is all real. It's because you can plug any little number into this equation and get out an answer. And our range is going to be y equals 1, or sorry, y is greater than 1, because, again, that always comes from our asymptote, because we don't touch it, but we come really, really close. It's going to be everything above that in this case. Okay, here is an exponential decay word problem. Give it a try. In our equation, if you recall, A is our original amount that we're starting off with. R is our rate. T is our time. Give this one a try. Okay, we should have got an answer of approximately $4,997.03. If you got that, yay! If not, here's the explanation. We plug all of our numbers in, so we have 13,500 times 1 minus 0.22, because again, we have a 22% We want to move the decimal 2 places to the left to write that as a decimal point. And then we want to graduate college in 4 years, so that's what our time is t of 4. So we subtract 1 minus 0.22 and we get 0.78. 0.78 to the 4th power is 0.37015. Then we take that times the 13,500 and we get the not so good answer, actually, because our card decreased a lot over those 4 years, of $4,997.03. Okay, now we're going to practice our logarithms. This is target 2, evaluating logarithms and graph logarithmic functions. Here we are just practicing rewriting the equations into exponential form, so take a moment, give those a try. Okay, now we know that our basement number, this 20, is our base of our exponent. Our exponent is on the other side of the equation, so we have a 2, equals 400. You don't need to check these. These are automatically correct. We are just rewriting them so we can get good at going back and forth between logarithmic form and exponential form. This second one here is 49. That is our base because it's in the basement. To the 1/2 power equals 7. And then the last one is 5 to the negative 3rd equals 1 over 125. What does that negative do? You remember? Huh? You got it? That switches it into the fraction. That's why this is down here on the bottom, that 125. That negative exponent flips it into a fraction. We're going to need to know that in a moment. Okay, so here are 4 problems that we're going to evaluate the logarithms and find out the answer. So give these a try, hit pause, come back and see if you got them correct. Okay, so we mentally set these equal to x. So this would be 7 to the x power equals 343. So if you don't know what 7 to the whatever power equals 343, if you don't know that power, then you can try in your calculator, do 7 times 7 times 7 until you get to 343. Or you could just have it memorized that 7 to the 3rd power equals 343. So 3 is our answer. Next problem. Log of base 8 of 1/64. So again, we rewrite it in exponential form. So it's 8 to the x equals 1 over 64. Well, it flipped from a whole number into a fraction. So that tells us our answer is going to be, yes, that's right for everyone playing out there. That means it's a negative. We also need to know what number, 8 to what number equals 64. Again, you should know that one. There's not really a reason to not know that one. But if you don't, you would take 8 times 8 times 8 times 8 times 8 until you get up to 64. You would have to do that 2 times. Our answer is negative 2. Okay, next one. We have log base of 16 of 256. So again, rewrite it into exponential form. 16 to the x equals 256. So 16 times 16 times 16 times 16 times 16, how many times equals 256? That's correct. It is 2 times. And then our last one is log base 3 of 1 over 81. So we set it equal to x. 3 to the x power equals 1 over 81. Again, it went from a whole number to a fraction. So what does that mean? Huh? What does it mean? It means that our exponent has to be negative because it flipped it. And then 3 to what power is 81? Again, something you should know, but again, if you don't, try it in your calculator. 3 times 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 3 until you get 81. You shouldn't have gone as far as I did. All you need to go is 4 times. So negative 4 is our answer. Next, we're going to be finding the inverses of the function. So we're going to use the stuff that we learned last unit in Unit 6 about finding the inverses to find the inverses of log functions here. So we have y equals log base 7 of x. What is our first step in finding the inverse of functions? Do you recall? Do you remember? Huh? Got it? Are you talking to your computer screen explaining the answer? Saying, Ms. Steele, just move on. I already know this answer. Well, here you go. You switch the places of x and the y. And then we write in exponential form. 7 is our base from the basement. X is our exponent equals y. And looky there. When we're doing inverses, all we want to do is solve for y. And we just did. Yay! So y equals 7 to the x power. Next one is y equals log base 15 of x. So again, first step, switch the places of the x and the y. So x equals log base 15 of y. We rewrite it in exponential form. So 15 to the x equals y. And that is our answer because we want to solve for y. I'm trying to move as little as possible because every time I move, the motion sensor goes off and the heat comes on. And I am dying of heat. It's like 80 degrees in this room right now. So I'm trying to get through this quickly without moving around a whole lot so the motion sensor does not come on. Not that you needed to know that, but I thought I would explain as to why I keep laughing. Because it's freaking hot in here. Okay, so now we have an exponential function, and now we want to find the inverse of this. So we have y equals 12 to the x. Crap, there it goes. Man. Okay, so we switch the places of the x and the y. So we have x equals 12 to the y power. We notice that y is our exponent, so we can probably write this in log form and have it be an inverse. So we have log base 12 of x equals the exponent of y. We just solved for y. Yay! Okay, next one. We switch the x and the y. X equals 23 to the y power. We write this in log form. So it's log base 23 of x equals the exponent of y, which is exactly what we want. Okay, we're going to end off with 2 graphing problems. So we're going to start off with the basic one. Y equals log base 2 of x. Give it a try. Remember with these, we do these a little funky. See if you can remember and then come back to check to see if you did. Okay, here is the graph that we should have come up with for this graph. Remember that you need to rewrite your equation in exponential form. So 2 to the y equals x. Now remember also with this one, because our y is our exponent, we're going to do the y numbers and we're going to plug those into the equation to get out an x, opposite of what you're used to doing in algebra and math class. So we're going to plug in 0, 1, 2. 2 to the 0 power is 1, 2 to the first power is 2, and 2 to the second power is 4. We graph those. We find our asymptote. Usually you're used to it being the Kelly point, but when you're doing logarithms, it's actually the Hank point. There is no Hank in this case, so that's why our asymptote is x equals 0. And it's x, because it's a vertical asymptote. Remember that with log forms. Our domain is x is greater than 0, because we have everything here on the right-hand side getting bigger. And then our range is all reals, because we can get any number out of this equation. Okay, we're going to do one more. That's a little trickier. It's going to be a translation problem. So give this one a try. See if you can remember the steps and then come back and check out your answer. This will be the last problem. Yay! Okay, even though this one's not completely done, I'm coming back for the explanation now. So what we have here is we do our base graph whenever there's a translation. We do y equals log base 4 of x. We turn it into the exponential form, which is 4 to the y equals x, and we do our xy chart over here, again plugging in the numbers for y to get out our x's. We also realized from our original equation that our asymptote is going to be positive 2 because that's our Hank value, so this is the green dashed line going on our graph. And then we plot the points 1, 0, 4, 1, and 16, 2. But don't connect the dots. Don't you dare connect the dots because that is not our answer. Now we got to deal with the translation part, our Hank and Kelly point, which is 2, 5. So we're going to take each of these green dots and move it 2 to the right, and 5 up. So this first one, 2 to the right, 5 up. 2 to the right, 5 up. This one's going to be a little trickier because it's off the graph, but I'm going to give it a try. 2 to the right, 5 up. 3, 4, 5, something around there. And then we're going to draw our graph. And there you go. Our asymptote, again, is x equals 0, and it's x equals, be very, 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 very careful. Our domain has to do with our asymptote in this case, so it's x is greater than 2, because we're getting all the x's to the right. Our range, because of these arrows here, that means we're going to keep going and going and going and going and going. So our range is all reals. So this is our review for our quiz 1 for unit 7, dealing with our basics of logarithms and a lot of graphing tonight. Holy cow, that's a lot of graphing. So good luck tomorrow and have a good night's sleep. See you tomorrow.